All right, so John and Finley, glad you could join us remotely at least. Hopefully you're doing well. We'll miss you guys and look forward to having you back with us soon. And Ethan, if you end up watching the video, Jackie, I'm not sure if you'll be here or if you'll watch the video, but we miss you guys. Hope you all had a good break. Just want to give a quick update on sort of the state of the AP Physics 2 address deal here, and talk a little about your exam, and then we're gonna wrap up a few little loose ends from Unit 3 on electric potential. That was the one concept that we really didn't get to dig into much. So we're gonna try to wrap that up today and tomorrow, and then next week jump into Unit 4. So that's kind of the plan. We'll see if we may need a little bit more than today and tomorrow to get through capacitance, but it all flows very nicely into Unit 4 because Unit 4 is electric circuits, and we're going to be talking about potential and capacitors and things like that. So it's a lot of connected value. So I wasn't too concerned with pushing it to this semester because it connects so well. All right, so first, just to update, I know many of you asked about my family before the break, and several of you said you were praying for my daughter who had all the health issues and stuff. They did on December 14th or something, right around exam week. They did move to Texas so they could be with her husband who's in the Army stationed there. The move went fine in terms of getting them all there. She had her baby yesterday, and baby and she are, everybody's healthy. So our house was very quiet over the break with she and the 3 kids and her mother-in-law all gone. It was just my wife and I, and our son came to visit for part of the time. So, but I appreciate you guys that were asking about that. Just wanted to give you that update that family's doing well. Got grandbaby number 6 here now, Ryan, and he's healthy. So that was exciting news yesterday. In terms of how class is going to have to operate, I think I got about 20 emails over the last couple days of students who aren't going to be here for one reason or another. Some of it's illness, some of it's other things. But I had, I think 6 or 8, I think all but one period, I have someone that was supposed to be on Zoom in just about every class. And so for the next week or so, I just plan on starting Zoom, using it if people show up. Great. I'm going to also try to record the classes. So if you have to be out for any reason over the next couple weeks, that is my plan, to just have Zoom running whenever we have a class, because it's going to be hard to keep track of. I think there's going to be always someone that's got permission to be on Zoom in almost every class. So I'm just going to have it running, and I'm going to record the sessions just because there's going to be people absent for a variety of reasons. So a reminder of how that works. Obviously, you guys are kind of experts in terms of Zoom, but the link is on the bulletin board page of Access. And also in the announcements is where I'll put a quick summary of what we did that day. So just a few bullet points of, I'll put the date and then like the agenda, what we covered briefly. And then also on the bulletin board, there's that links section where you can link to positive physics, or you can link to AP Classroom and those kind of things. There's also a link to my teacher YouTube page. And so I'll be posting those there. That's, I think, the easiest place for students to access. So just go to the bulletin board page, click on my YouTube channel link there, and then there's a different playlist for AP2, AP1, and CP. So just go to AP2. I'll title it by the date. And so if you have to miss, you know that the recording will be there. If you're able to attend virtually, the Zoom will be running. We are in a good spot time-wise, but we do need to keep a good pace. So just like we did first semester, maybe even slightly tweak it up so we have a little extra time to review. It's nice this year that the physics exams are in the second week of the AP cycle. Last several years, it's been in the first week, which cuts down our time. But now we've got a whole extra week that we've had in the last 4 or 5 years. So I'm excited for that extra little bit of time, but we will need to go at a good pace. So if you do have to miss for whatever reason, make sure that you're taking advantage of every opportunity to not fall behind. In terms of your exam grades, I was quite pleased with the results. Overall, the scores were very high. You did get kind of a double curve because there was one question where there was a typo. There should have been parentheses around part of the answer, and most of you got it right anyway, but I still, when there's something like that, I feel like it's good to throw that question out of the mix. And so I did take that question out of the equation entirely. So that was like a free question, whether you got it right or not. just reduce the points possible, which improves your percent. And then you also just got the traditional AP2 curve, which isn't quite as steep as the AP1 curve, but it's still a pretty nice one. So if you've looked at your grades, that there was a kind of a double curve. One was just a small change of that. Because of that typo, I wanted to give everybody that benefit, and then the normal curve on top of that.
Will we see our tests or no?
We won't be taking any class time to do that, but if you ever want to come in, because my family situation is a lot more stable now, I don't expect to be like bolting out after school to get home to watch the grandkids or anything like that. So I should be around after school every day, and lunches I'll still be pretty free almost every day. And so anytime you want to come in, I do have them in here because I figure probably some students will want to take a look. And so if you want to do that, you're welcome to just come in during lunch, come in after school, and I'll keep them up here in the room for probably a couple weeks, and then after that, I'll store them in the locked file cabinet downstairs. So yeah, the next couple weeks, if you want to come and take a peek at it, you're welcome to. Any other questions about schedule or the exam or anything? All right, so like I said, the goal is to try to wrap up those little 2 concepts on Unit 3 this week, hopefully jump right into Unit 4 next week and on circuits, and then we kind of switch gears after that, and we get into some magnetism, and we get into electromagnetic spectrum with light and reflection and refraction and lenses and mirrors and all kinds of fun stuff. All right, so let's move on then. So these are the basic points, and we've talked about some of these things. Like we've talked about potential energy in AP Physics 1. We've talked about voltage. We've talked about electric fields, but the real clear definition of electric potential and the idea of capacitance and capacitors are what we need to touch on. And so those are sort of the ideas we still need to cover. And I want to start with a AP video and just watch it together. It's from 310, and I noticed that it said 0% of the students had watched it. So on almost every video, most students or some students had watched it, but this is one that nobody had watched it yet, and I think it's a good review and also a good definition of potential. And so we're just going to watch this one together, kind of get us rolling here, and hopefully it'll work well for you guys through Zoom. I mean, you could obviously watch it on your own too, but let me switch the share here. Go to this, share the sound. Hopefully that works. And hopefully it's going to show up. Yeah, I like this little feature up here for the teacher. I can see how many have watched and who's watched. And so as I was kind of reviewing and going back over some of the videos over the break, I was like, oh, no one's watched this one. This one's really good. So we'll just use this as a warm up if I can get it to work. It did say that the computer was struggling a little bit. There we go. All right. So Finley and John, let me know if you can hear this okay through, it should be coming through the system, so hopefully that'll work well.
Hi everyone, Mrs. Besega here from Glastonbury High School in Glastonbury, Connecticut. And look at a new notation. That notation, which Mrs. Rednick already chatted.
Let me see if I can get the volume turned up a little bit more. The TV's volume's up, but.
With you about represents the force per unit charge. Electric potential, it's important to have these 2 distinct representations of the same phenomenon. So let's look at an example. Let's take a look at gravitational field. Now, someone was asking me, why didn't I put dots at each of these locations? And I didn't want you to think that the locations needed an object there. So rank the magnitude of the gravitational field at each location near the surface of the Earth. A is on top of a mountain, B is on the surface of the Earth, D is a little bit above a lake, and C is up in the air.
What do you think? This is gravitational field, or another way to say that, the value for G. Any ideas?
Is it B?
What's that?
Is it B?
Well, they're saying rank them. Oh. So the magnitude of the gravitational field. Give you a hint, it's a little bit of a trick question.
Wait, are C and A like equal distance?
Mm-hmm.
Let's see.
Yeah, it is. We're not talking about gravitational force, just gravitational field. All right, not a lot of confidence in this, so let's let her talk you through it.
Pause the video. Think. Okay, here's what I got. I'm thinking magnitude of gravity, all of them. The magnitude of the gravitation, that means if I went and put a mass there. Then, so let's go put a mass there. Let's A, and now the dots are representing my water bottle. Rank the locations in terms of the gravitational potential energy stored in the Earth bottle system at each location now.
So now we're talking about gravitational potential energy, not the gravitational field, but the gravitational potential energy. So she's helping you review some AP Physics 1 stuff.
So are A and C like on the same height?
Looks like.
Okay. So A and C are gonna be like the greatest, and then D and then B.
Then B, then D,
D and
then D, then B.
Yeah.
Okay, and how did you determine that?
It's like the height thing.
The height thing, good. Anybody remember the equation for gravitational potential energy?
MGC.
mgh, and since g is going to be constant and they're all a 1 kilogram bottle, the only thing that's different is the h, right? The only thing that's different is the height.
Same gravitational potential energy. Surface of the ground. So A had more gravitational potential energy than B. That gravitational potential energy depends only on height. For the same, this was the idea behind the electric field notation that Mrs. Rudnick was talking about in the last video. Now you and I can experience the electric field. Let's say there's a Van de Graaff generator. It's accumulating a large negative charge through the use of the belt you can see spinning inside that clear plastic over there. And I can feel it on the surface of my skin, moving the little hairs on my arm, but maybe you can't see those, so we'll use fur instead. Electric field distorts the space around that sphere. And we talked about last time that we could represent this with a field diagram.
So I want to emphasize what she just said there about that an electric field is a distortion of the space around a charge. And that's really what gravity is. It's a distortion of the space around not a charge, but an object with mass, right? So an object's mass distorts the space around it. I don't know if you've seen pictures or videos where they have like an object sitting on like a stretchy fabric that shrinks it down and kind of makes a funnel sort of shape, and try to talk about gravity that way. Charges do the same thing. And you guys went through that whole kind of long process with the PhET, right? Where you put charges all over the place and looked at the fields and tried to draw them and figure it out. And every time you put a charge in, it distorts the space around it. Okay, so keep that in mind as we go through this whole unit and a half, or unit and a tenth, I guess, as we wrap up 3 and get into 4.
Now we'll talk soon about how much force each unit of charge, each unit of space, and we would represent it as a vector. Charges, you know the deal. Later we'll talk about how we would need to add these as a vector sum, because electric field is a vector. Just like in this picture, we're showing vector sum addition because I have 2 electric fields pointing to the right. The net electric field would be the sum of both of these. If we had one pointing to the right and one pointing down, I'd need to add them with Pythagorean theorem. And if they are multiple, I could use clever choices of variables in order to get the net electric field. In this case, I would see the x components of electric field cancel to give a net electric field up. More on that later. So one representation is electric field. Why would we need a new representation then? So let's talk about electric potential. Electric potential is proportional to energy. It tells us the electrical potential energy per unit charge at a point. This is a scalar quantity, and that means I don't need to bother with cumbersome vector addition when choosing coordinates and canceling x and y components. Scalar quantities have no direction. In this case, a positive sign in potential just means that your point is near a positive charge, and they add as scalars.
All right, so a couple things, I would encourage you maybe to jot a couple of these things down into your notes. These are some important, there's a good definition here, a couple facts that you definitely want to remember. So when we talk about electrical potential, it is the potential energy due to the charge per charge. Okay, so it's electrical potential energy per unit charge. How do we define electric field mathematically?
Like the force except without the other charge in it.
Yeah, it's the force per charge. Right, so similar definitions. Electric field is the force generated per unit charge. Electric potential is the electric potential energy per charge. So they're similar but different. So when we talk about electric potential energy, we're going to use the letter U again, like we saw in AP1, or use U for potential energy. And if you look on your formula sheet, I'm going to show you another one here in the notes, but it gives you an equation here for the electric potential energy as Q times delta V. And so they use a little E here to let you know it's electric potential energy, and then it's the charge times the change in potential. And so what we're saying here definition-wise is that change in potential would just be the change in electric potential energy per unit charge, okay? Field, electric field, is the force per unit charge. Okay, so they're similar. This is the way you see it on the formula sheet, these two. They're similar, but this is how we're seeing potential, because voltage is what we're defining as potential, okay, what we measure potential in. What are the units for voltage then based on these variables? Joules, energy, per coulomb, charge, right? So a volt is a joule per coulomb, okay, based on this relationship. Again, you'll see it here on the formula sheet, but I would challenge you to think about it this way, just manipulating it algebraically, for two reasons. One, it tells you the units for a volt, okay? It also often is something where you're going to be taking this relationship and substituting it in for V on a lot of problem solving. Okay, so it's the same equation that they give you, but you're going to be manipulating a lot to solve a variety of different problems. The other thing that's nice here is because it's energy, it's a scalar. Direction doesn't matter. We do still use positive and negative signs, but we put a positive sign on it if it's near a positive charge. We put a negative sign on it if it's near a negative charge. So it's just telling us about proximity to the closest charge we're considering.
We often draw lines where along that line would have the same electric potential. Similar to electric force and electric field, one charge starts just one Q, and it goes more on that another time. Electric potential is electric potential energy per unit charge. So another representation mathematically could be that your electric potential is a charge. That means that 1 volt is really equal to 1 joule of energy per coulomb of charge. Now, just like gravitational potential energy always had a 0 point, which we usually define as the ground, right? Electric potential is going to similarly have a position defined as 0 potential. We usually call it the point infinitely far away. Notice that if this were a negative charge with these negative potential isolines nearby, then I would need to be infinitely far away to stop feeling the effects of the electric potential as the difference between 2 points, and we'll get more on that later.
So she's mentioned isolines a couple times. Just want to make sure you understand what we're talking about here. So you've done field diagrams. We spent quite a bit of time drawing those field diagrams and how the arrows point and create different shapes of the field. Isolines are the centric circles if it's a single point, if it's a capacitor or a plate, kind of like what you did with fields, it changes the shape. But isolines are, what would the voltage be? What would the potential be at various distances from that point? And so it's a little bit like a field concept, and that we're going to represent it sort of graphically. But we call these circles here isolines. And if it's a single point, it will be concentric circles. If it's a plate, then we're going to see like almost like a tide of the ocean coming in waves. Okay, we'll look at some different examples of that in the future.
So what should we take representations of how to imagine this throughout this video? It is super cool. In this video, this would be a three-dimensional model of giving positive potential. Viewed from the top, it looks like two circles of positive charge surrounded by negative, and the two negative charges give a negative C.
We talked about how charges distort the space around them, and this is a graphical representation of the positive charges creating a distortion in one direction and the negative charges creating distortion in another. This is what we would call a quadrupole. It's got 4 poles, 2 positives and 2 negatives, kind of in the 4 corners of a square.
We could picture this as electric field. So this is the same for electric field because it's a vector, is useful for studying vector quantities like force and acceleration. On the other hand, electric potential is related to potential energy. Just like we studied gravitational field versus gravitational potential energy, well, it's going to be useful to study electric field versus electric potential. In this case, electric potential is useful for scalar quantities such as electrical potential energy and speed, as opposed to the vector quantities. So tune in next time with Mrs. Rudnick to learn more about electric fields. Bye now.
All right, so good video and lots of good information here. So we're not going to watch all of these videos. There's tons of them. I think I'll probably end up showing you maybe 2 more out of the 20 some videos that were in Unit 3. But there's a couple that as I was reviewing, I was like, man, these are just real succinct, good visualization, images and things that I don't have access to. So we will look at a couple of those over time. But I wanted to start with this one today as a nice review. All right, so I would recommend that you go back and check those out. That would be a great way to kind of review the unit information from Unit 3. All right, now let's dig into a few slides of notes here to wrap things up. So let's see, raise this up just a little bit. All right, can I get someone to read this slide for us? Hey, John.
Start with 2 positive charges initially at rest, with Q at the origin and Q at infinity, or big Q at the origin and little q at infinity. In order to move small q towards big Q, a force opposite to the Coulomb repulsive force, like charges repel, needs to be applied. Note that this force is constantly increasing as little q gets closer to big Q, since it depends on the distance between the charges. R and R is decreasing.
All right, so you can see that we've got our force equation down here. We've got our Coulomb's constant times the 2 charges over r squared, but in this case we have something moving. So what they're indicating here with this notation is that how would we recognize this as the radius is changing, right? So we could either do an infinite number of calculations, right, at every possible distance, or what else would be an option mathematically? Use calculus, right? All right, so we're not going to use calculus in this class, but they're going to mention it here as we go forward and break this down a little bit. All right, can I get someone to read this one for us? Ian?
Recall that work is defined as work equals force times the radius parallel to the direction of the work. To calculate the work needed to bring Q from infinity until it is a distance r from Q, we need to use calculus because of the non-constant force. Then use the relationship change in electric potential equals negative work. The work is done by the electric field of charge Q by definition on charge Q. As Q moves opposite the electric field of charge Q, negative work is done by the field.
All right, so in this case, what should happen to these charges? Should they attract or repel?
Repel.
They should repel, so they should go farther apart. If we're pulling that positive charge in, we're making it do opposite of what's natural, correct? So that means we have to do work, right? We would have to do work on this system to bring it in. And so the change in potential energy would be equal and opposite to the work we would have to do to bring that charge in closer to the big Q charge that's fixed, right? And since we're going opposite its natural direction, we would say the work is negative and the change in potential energy would be magnitude-wise equal to it. All right, we get someone to read this one for us. Okay, Tiger?
Work and potential energy. Assume that the potential energy of the QQ system is 0 at infinity, and adding up the incremental force times the distance between the charges at each point, integral calculus finds that the electrical potential energy, UE, is UE equals K times big Q times small q over R. Q is moved towards R at a constant velocity so that there is no change in kinetic energy. The sum of the forces due to the electrical field and the external force must be 0.
All right, so in this case, they're saying, it's kind of one of those thought experiments. Like, if we just put these charges in there, they're not gonna accelerate towards each other, right? So if we want it to go towards each other, we have to apply a force. And if we apply a force in such a way that we can cause it to move at a constant velocity, we'd be accelerating it overall, but moving it at a constant velocity towards K. We're, again, kind of thinking of a thought experiment of how we could define this mathematically, and also trying to help, for those of you that have calculus, maybe make that connection here. All right, someone read this one for us.
I can read it.
All right, Carter.
This is the equation for the potential energy due to 2 point charges separated by a distance r. UE equals K big Q little q over r. This process is similar to how gravitational potential energy was developed. The benefit of using electric potential energy instead of the electrical force is that the energy is a scalar and calculations are much simpler. There's no direction, but the sign matters.
All right, so conceptually here, a reminder of a few things that the lady talked about in the video, but mathematically here, just reminding you that last year in AP1, when we learned about gravitational potential energy, we did the same sort of thought experiment, but starting at the ground as our 0 point and then raising it up. All right, so similar sort of strategy here that they're using. All right, I'm gonna have to move this down here for now. And can someone read this one for us? Hey, Jason?
Again, just like in gravitational potential energy, electrical potential energy requires a system. It is not a property of just one object. In this case, we have a system of 2 charges, big Q and small q. Another way to define a system is by assuming that the magnitude of the Q is much greater than the magnitude of small q. Thus, the electric field generated by big Q is also much greater than the field generated by small q, which may be ignored. Now we have a field charge system, and the electrical potential energy is a measure of the interaction between the field and the charge field.
All right, any questions so far? Are you following with the sort of train of thought so far? Okay. Next. And Finley and John, if you guys have active microphones, you're welcome to jump in and read as well if you'd like. Someone read some for us? Okay.
What is this electric potential energy? It tells you how much energy is stored by work being done on the system, and is now available to return that energy in a different form, such as kinetic energy. Just like gravitational potential energy. If 2 positive charges are placed near each other, they are a system, and they have electric potential energy. Once released, they'll accelerate away from each other, turning potential energy into kinetic energy. These moving charges can now perform work on another system.
All right, so if we go back to this picture here that we've been kind of looking at, I would have to do work on this small q charge to push it closer to this big Q fixed point, right? And so as soon as I let go, it's naturally going to repel and go back the other way. So we are storing the potential energy in as we apply a force that moves it closer and closer. that make sense? All right, so back to the flow here. Bring this back up. Someone want to read this one for us? Hey, Tiger.
Electrical potential energy. A positive charge and a negative charge have a negative potential energy. Positive work is done by Q's electric field on Q as the charges are attracted to each other. So UE equals KQ times negative Q because it's negative over R, and it's also equal to negative KQQ over R. It takes negative work by an external force to keep them from accelerating towards each other. The sum of the forces on the charge has to equal 0. The potential energy of the system decreases as the charges move closer to each other.
All right, so they're just here clarifying, okay, you've gone through the whole, what if we got a positive charge being forced to get closer to a positive charge? What about if that test point was negative? It wouldn't be repelled, it would be attracted. So we would have to apply the force in the other direction to keep it from attracting in and reaching that positive fixed point in the middle, which doesn't change anything mathematically other than the sign. Because now the work we're doing is positive work because we're pulling it away, and now the energy would be given the negative sign, okay? So again, it's a scalar. Work and energy are scalar values, but we use the signs to indicate how the direction of movement and the force being applied is different. So in this case, it naturally wants to move to the left, so I would have to apply a force to the right. All right. Next up, someone read this one for us. Just kind of a quick summary. Okay, Ian?
Two positive or two negative charges have a positive potential energy. Negative work is done by Q's electric field on Q. The electric potential equals K times big Q times little q over R. Or the electric potential equals K times negative big Q times negative little q over R, which equals K times big Q times little q over R. It takes positive work by an external force to move the charges towards each other. The potential energy of the system increases as the charges move towards each other.
All right, so we're storing more and more energy as we move them closer to each other. And if we let them go, then that energy would become, instead of being stored as electric potential, it would become what? Kinetic, and they would repel and move away from each other. Okay, so you remember doing all the bar graphs in AP1? All right, that would be how we could represent this here. We're initially doing work to store electric potential energy. Once that force is taken away, that electric potential energy is going to convert into kinetic energy. And thinking through those bar graphs. Yeah, kind of like a spring. In fact, I don't know if some of you probably knew Miss Turk, who used to teach here. It's been a few years, so maybe not. But one of her phrases that she liked to say in her physics classes that she was teaching is that everything's a spring. If you stop and think about how everything works, it almost all works like a spring, even though it's not technically what we think of as a spring. And so it's a good observation. All right, number 14, or sorry, number 1 here. Let's do a calculus, slide 14. So let's see if you can figure this one out here based on the equation. And I will say, this equation that you see on the previous slide, this KQQ over R, that is not on your formula sheet, but it is one that I would recommend that you write down. So I'll give you a couple seconds. You probably want to write this one down wherever you're keeping those extra little equations that are handy but not provided. They do have an equation for electric potential energy, but it's not this format, and this format is particularly helpful for certain kinds of problems. So one way to calculate electric potential energy is to take Coulomb's constant times the two charges divided by the distance between them. Now, you might recall that that's very similar to gravitational potential energy, that one way to calculate gravitational potential energy is to take the gravitational constant times mass 1 times mass 2 over R. So it's a similar relationship that we learned in AP1. All right, so let's have you, I'm gonna pass back these lab reports for you here while you're solving this question. Well, I think some of these were just corrections and late reports, but. Maybe it's Jackie's. So when you guys did that electric field mapping, David and Sean, did you guys work with Jackie? Remember? You don't remember? Like drawing all these diagrams from the FET, do you remember who you were working with?
No, I was working with Tiger and Jason.
Okay. Sean, do you?
No.
You remember who you were working with?
No, I was working with David.
Oh, okay. Oh, Eagle, with the, back in the fluids lab, did you work with Jackie? Yeah, back in the day?
I think so.
Okay, this must be his then, there's no name anywhere, but I think when he turned it in, I knew whose it was, and so I just, figured out, or maybe it's the only one that was
You
missing.
write any like lab partner, I think?
He wrote his lab partners, but he didn't write his own name anywhere.
Oh, but like, I think I'm the partner for like most of the lab.
Yeah, okay, the first few, it was you, so,
Yeah,
I'll bet this must be his, okay.
Where was Sean? Where was Sean? Oh, Sean's sleeping. Oh, we went over.
Alright, anybody have an answer for this one yet? Been able to figure it out?
Did you see the Instagram?
Is that, what letter is that, A?
Yep.
A? Alright. So let's check the results here. We use our two charges with the Coulomb's constant and the distance between them. A is the correct value. Alright. Alright, so we're about out of time, and that's about where I wanted to get. So there's have a couple other example problems, but they're the exact same work. So we'll maybe start with one of those as a warm-up tomorrow, and then go further into this whole idea of potential energy versus potential. Again, if you haven't watched many of those Unit 3 videos, highly recommend it. Good review. And the only ones we're gonna look at, I'm gonna look at one of them from section 11 and one of them from section 13, possibly one of them from 12 on isolines, but most of them we will not be watching together. So it'd be good to review that. And Finley and John, glad you guys could join us at least virtually. Hopefully you guys are able to come back and be here in person with us soon.
Thank you.
You're welcome. Well.